This is a discussion of rate laws for what we call second-order reactions. In these reactions, two molecules of A are colliding to form one molecule of the product B. The rate law we ascribe to this is the rate is equal to a constant times the square of the concentration of A. That is, B is appearing at the same rate that two of the A's are disappearing. Let's see what results. We're going to assign an original concentration of 1.5 molar to A. In other words, we're using the same terms as we did in the other two videos. In the first second, there is a 0.11 molar reduction in A and a 0.06 molar increase in B. Remember, you need two A's to make one B, so this is disappearing twice as fast as B is appearing. In the second the rate is somewhat lower because the concentration of A has gone down. But again, we are losing two of the A's for every appearance of a B. After 40 seconds, it's easy to see that if there's been a very steep decay and a steep increase in product, but not as steep because, again, you needed two A's to make one B. Over the same time period, if we plot the natural log of the concentration of A versus time, you can see very easily that this is not a straight line. If we try to force a straight line, we get a correspondence of only 0.958. Remember, we need a correspondence very, very close to 1 in order to say this is a linear relationship. It is not a relationship that is linear, natural log of A versus time. However, as we suggest in the textbook, the reciprocal of A versus time does give you a linear function, and K is the coefficient. Here it is, 0.05, the coefficient that we assigned to the rate law. If we reduce the rate constant, we slow the reaction down, but we get the same difference in the shape. This is not a mirror image of the decay curve. And if we increase the rate constant to 0.1, we see the same kind of thing happening. We get a very steep decay in A and a somewhat more rapid increase of B, but again, this is not a mirror image of A.